Hi there, welcome back. So this point we have covered a lot, and let's move to the last step. Now, previous videos we covered the MRF, multiple reference frame. We add the sourcer in this region, but we didn't put it into motion. So now let's put it into motion. So pretty much are the same steps. Now we're going to see how to put it into motion, and that's all. Okay, hopefully we know everything will be quite easy, quite fast. So basically the idea is to do this. The propeller, put it into motion, and then get your solution. What you see here is a less simulation. The case that we're going to work, it is this one. Okay, it's ready to go. I'm not going to run it, as you can imagine. It's quite expensive, very time consuming, but you have there and you can run it, and if you have enough resources, it can be something relatively fast. So I recall I run it like more than 200 cores, and it was 2 days. Okay, in a mesh, something about 8-10 millions. So remember also we covered something about this intersection here. It's important, be careful about that. So now let's move now to the actual case. So let me go here, close there, and open here. So we're in the folder. So just to remind you that we cover here first case, no sounds, nothing happened there, fix. Then MRF, we added this region, and now NCC, we have that region. We're going to do a separation, and then we could put it into motion. As usual, we have same data structure, okay, the case, and let's visit here. So let me open the scripts, run mesh. Then after run mesh, so let's see, be careful that I'm running here the quartz mesh. You have the fine mesh, one you can run, but it's time consuming. The 28 cores, also change it according to your resources. Everything coming here. So we're going to use the zero pitch propeller. Also previous video we studied changing the pitch angle, and we saw the influence, so we gave a physical meaning. And the same observation that we saw in the MRF, you're going to see here. You will see the improvement when you change the pitch up to a limit, and then it will change. We'll read the region, and up to this point that we do the mesh. Okay, everything is the same. The extra step that we have now is that we need to run this script. Okay, that we also the NCC. We also did it with the MRF, and we saw that using the NCC improve the results in the MRF in the intersection between the regions. Here we don't do it because we need to improve that. We need to do it to do that topological separation and then put the mesh into motion. Okay, so we're going to study these steps, but pretty much the mesh is the same. This will be the main difference between all the other approaches. Then we can run the simulation, or we can test the kinematics that we're going to see that. So we have this script, and this is to run the simulation. Okay, so let's run the mesh. Let me go here, let me load OF12, run mesh. And this mesh, let's see what we're going to do here. This script, we have several scripts. Okay, so pay attention that in this case, we're going to do the script, but the script is also doing the mesh, the boundary layer at the same time. Okay, so to have that the transition of, we have the body and the propeller, so we have everything. But remember, you can do this also in individual steps, separate steps now. So you can do just this mesh there, and then do the BL. You have here the script also. So I put it all together, and I put it all together because I know at this point we know very well what is happening. We know that this script will work fine. So let me open this script. Let me go here, run this one, what is running in background. Let's revisit the script. Okay, there is nothing to comment, the 3 steps here. So as I say, I'm doing everything here, okay, in the animation time, because we know what is happening. Then read the geometry, very straightforward. So you have your geometries. Remember that body STL, we already all the manipulation in paraview with intersect surfaces and so on. So it's up to you. We have the propeller, the rotating region, refinement region, and if you want to load more STLs, it's up to you. Very straightforward. Remember that you have different options here. We're just seeing the simplest option, the ones that you are going to use most of the time, but you have different keywords there, but I don't want to comment on that. Not necessarily. Then we move to castellation, which is the Cartesian mesh. Okay, we do all the cell addition here. Okay, then also there is some old cell addition in the boundary layer, but all the cell addition for the surfaces, edges, and regions, volume regions is done here. So as I mentioned, this is pretty much a standard. The only thing that you need to be careful about this one, according to the maximum number of cells, you just increase that one. So if you put there 1 million, you are not going to get a mesh with more than 1 million. So it's up to you. To start something that, remember that Snap is very, it uses a lot of memory. So if you're going to do large memories, better have a node with a lot of memory, okay? Then features, okay, these are the edges, remember. So here we capture all the edges, so it's up to you. We saw how to do it using surface features, how to do it using also paraview, also how to do the intersection between surfaces. We will look at that command, that application that we have in OpenFOAM, that you can do it. There are also Python scripts and external programs to do that, but let's keep everything integrating within OpenFOAM. It works very well not using that application, or you can do it also in paraview with no problem. Surfaces, you apply refinement your surfaces, so we have seen that. Okay, so it's up to you. Then rotating, and this is the important step when you want to do MRF or put things into motion. Okay, so here you need to create that region. So you have two methods, method 1, method 2. I prefer to use method 2. Now this is very straightforward. Just select rotate, and this corresponds to the region that you want to put into motion. So for us, if we go here, it is this region here. So you create that, you read it, then read the geometry, and here when you assign the surface, put it there, move inside that geometry, and then create the cell zone and the face zone. So now that you have this information, you can use the cell zone to apply the sourcer, and to create the NCC, you use the face zone and do all the manipulation. We're going to study that. So very straightforward. Then we move to regions, okay, which are volumes. Apply your volumes. So remember here also in volumes, you can apply, you can use a surface to apply a refinement, and then use distant mode. Okay, so this is what I call, we studied in the previous video, those surface refinement on top of the surface. So it's better to do it like this. Do not do it here. Now, for instance, you have prop, and then you select in the prop at a specific region to do a refinement. It is going to work, but then it's going to give you some issues, some problems now on creating those boundary patches. So in that case, just apply it here. Okay, so to make it clear and to recall this one, so let's say for instance that you have your airplane, and let's say that in that airplane, now you select and see it there in orange, you want to select now the elevator here. Okay, so you have the elevator, you select it. It's not that you are going to read here. Now look at that, you have the surface, the body, which is the whole airplane, and then you have the elevator, and you apply another refinement in that elevator. It's going to work, but it might give you some issues when naming boundary patches. In that case, it's better to apply that elevator here. Okay, that is a trick of my own. Okay, I highly recommend you to do like that. Then mesh selection, well, this is where what you want to mesh inside, outside. Very straightforward. Now it's not controls. I'm not going to comment anything here because for me this is a standard. Okay, so this is where you are doing all this snapping from the Cartesian mesh to the body fitted. Very important also, previous video we studied the suction and we saw that it has an influence. Also recommend you to use explicit feature snapping, that is that you need to compute it with an external tool and then you read it in Snappy. These are mutually exclusive, so don't put true and true. It's going to give you problems. Probably it's going to take by default implicit, if I would recall. It is mutually exclusive. So this one is off, this one is on. Okay, and vice versa. Then you move to add layer controls. We studied this, okay, a lot. This is the tricky part. Now, as I say, snap is a very good measure up to this point. At this point, it can become tricky if you want to have very fine inflation layers. But inflation layers, boundary layer meshes for wall modeling meshes, it works very well. And that's all. The rest of the options are optional. Now your mesh quality parameters, and then save some debugging file. So this is it. As you see, very straightforward. Even if we have this geometry that, let's say, that is a little bit tricky, okay? And what makes it even more tricky is that it's not a perfect geometry, okay? It's not a water type. We have then compute the intersections and some issues with curvature and mesh smoothness and so on. It works very well. So at this point, we have a mesh. Then let me go here. I have to check mesh as always. Check the mesh quality and see that nothing to complain about. Okay, so probably skewness 10, that is not an issue. And orthogonality also will tell you, but 70 is very good. So, and 10 probably a little bit higher, but something that I'm not worried about. And a few cells, I know that I make it finer, likely would be much better. You know how to visualize those cells. I'm not going to do it. Okay, previous videos we talk about that, but let's take a look at the mesh, okay, to revisit. And actually, it's not this. Let me go and open paraview. Okay, so I go here, paraview. Remember that in paraview, when you use this option, you have this plugin there. You can read the steps. And what I want to show you is that all the steps, now that we're computing, even the back quality cells, you can access that and visualize that. But I want to show to see is this one. This is the, recall that at meshing time, and let me close here. And to be sure, at meshing time, we created these regions there. Here, you can access those regions. So you have the cell zone, so you can apply your MRF there. And then you have the face zone. No, those are the faces. And you can use this, okay, to split the mesh. Okay, so far we have a single mesh. Okay, so you can split the mesh and then disconnect this internal domain from the external domain and put it into motion. So that's what we're going to do now. So let me show you what we have there. Let me go here. Oops. Let me put it here and change the color. And there you go. So inside you have the propeller, everything, and that's it. You put it into motion and we're ready to go. So the next step on revisiting this, now that our next step is this one, okay, NCC, now the non-conformal region. So basically here, let's revisit it step by step. So after we have a mesh, it can be the mesh with boundary layer, whatever is up to you. Here we know that is everything is working. Create baffles. Okay, so basically let me go here, system, and in this case create baffles. Okay, it's reading this dictionary, and look at that, what we're doing using the fashion, okay, that we created at meshing time, rotating face, also to stress this NCC. In this case we're using it that we have axial symmetry, now that axis symmetry that we can put it into rotation, but also you can have, you know, for translation, linear motion and so on. It can work in this case. But what is important that this case that we're going to do axial symmetry we have. So the name that you gave at meshing time, and then using that name create two additional patches, NCC1, NCC2. Okay, you have these two patches. So let me run this step. I'm not going to run everything automatically. I just want to run, I only want to run this case. And let's see what we have. Okay, paste, and there you go. So it's going to read your dictionary, the mesh, and at this point we're going to have the NCC patches. So you're going to see that immediately constant polymesh, remember that you have this boundary file and see that you have the patches there, okay? Then you can also open paraview and you can visualize those patches. I'm running in serial, you can run this also in parallel. However, personal experience, I prefer to do all these operations in serial, okay? Large meshes, it can be time consuming now, but I prefer to do those operations in serial. And this is it, okay? So you have there your two regions, so NCC 1 and NCC 2, okay? But these two regions, okay, at this point, they are still connected, okay? In theory, you can try to put the mesh into motion. So if I go here, run mesh, this is a command to put into motion. So let me do something, copy this to, okay, paste, to use the dictionary for the motion. Now it's a larger time, so that's all. Let me paste this one. And okay, why we are 12. Moving, okay, phone run. Oh, it's here. Forgot. Okay, put it here, moving mesh, and this will move. Okay, the mesh has been contracted with anti. Okay, I don't need the FB constraint. Why is reading this one? It shouldn't be reading that one, but let's see. Okay, so now it will start to move, so it's using a large time step, but look at that, immediately you have all these errors. By the way, also I will comment something now that I have the checkMesh in every time step. So it is running, but eventually it will crash. Okay, the mesh quality will be too bad. It's already super bad. Okay, but at one point it will do a super crash, because when I move in here, those two patches and the regions, they are still connected. Okay, I haven't done the topological separation. So I'm going to stop it here. Okay, I don't want to keep running to waste time, but just to show you what is happening. And let me go here and let me just read prop. Okay, the propeller. And if I press play, you see that there is some rotation there. And at this point, it seems that, okay, things are all right, are working. But let me now put their NCC and with edges. And the issue here is that what is happening is that these patches, these regions are connected. Okay, so let me go here, put it this, and in this case I want to see only that, and here, okay, let me better go wireframe, and here I go like this, and hopefully you see what is happening. Okay, let me put the second patch. Okay, so see that the two patches, nothing, you don't see the second patches because the two are connected, and the two also are connected to the volume mesh, and they are just dragging all those cells, and eventually it will crash. So now let me go on phone list time rn. Okay, let me cancel that, and let's do the second step. Okay, so we're still in CC here. We understand that we're just selecting the face zone, creating the two patches, but now let's work this. Let's use this step. This step is split buffers. What it's going to do is disconnect those two patches, NCC1, NCC2. Now they are disconnected, okay? So as you check boundary file and so on, the stuff is still the same, okay? You have same names, nothing new. Later we need to use another command because these patches, we need to create new boundaries there. But if we keep reading here, at this point, it is okay. You have this optional command. I like this command now because you run here, you put it there. So when you put it there, it will tell you the regions, how many regions do you have. And here it's telling you you have 2 regions. So rotating cell, we know the one we're creating, and then this one with the default name. If you run this command before split this command, you will see that you have here just 1 region, okay? Even you have the set zone, you are going to have here 1 region. You haven't separated your domain. So at this point, if I run now again my phone run moving mesh, you're going to see that we're not going to get the same errors as previously, okay? So you have excused and everything okay, but the others, okay, it's much better than previously. You have also, you are showing, where I'm showing here many other quality metrics that you don't need, but this is working fine. It's not as the previous case. To mention something about that is important, let me open the control dictionary, okay? Because now this is something functionally relative new now that you have it here. So you put it and it will run checkMesh according to your frequency and whatever you want. So here, the saving frequency also will save the faulty sets and so on. And a very important set that represents the coverage of the mesh. You know, how good is that coverage, the splitting the for the mesh. So let me step here and okay, let me also cancel the last one, sometimes give problems, and let's visualize our mesh. So pretty much the same visualization we did previously. So let me open this too. Let me go here, put it wireframe, and let me change color, solid color. Let me put it here, black. So if I advance the next, look at the difference. So recall that in the previous, it was moving, but the both, look at that, remember that you have 2 patches. Both patches were synchronized at the same time. They were moving, they were connected. Now, there is 1 patch that is fixed and the other is moving. So what is happening, there is an interpolation from mesh to mesh. So the NCC, this method, what it's doing is that interpolating and doing some weighting of the fluxes and so on. Okay, so something that is for you that is very evident now is that the better the matching between these 2 meshes, the better that interpolation will be. So that is another standard practice. Now when you are doing that, try to have similar meshes, okay? Because sometimes you can control this, even that you have 2 patches. Let me move to the last one. 1 patch can be completely different from the other one. So look at, for instance, here, that one is moving and you are in this region and you're interpolating from small cells to another large cell. So that might not be a good interpolation. So one technique might be all this region, make it finer in such a way that that interpolation is always good. Something like here. So look at that close to the body, all that. So see that everything is the same patch, same dimension. So as you move, the interpolation is a good one in that region, but then a little bit far here in this region is not a very good. So you can do something like that. We have seen how to do that. So at this point, this is it. It's moving, we disconnected everything, and we go to the next step, which is very important, this one. So remember, this is optional. I like to do it just to check the regions and so on, but nothing new. But probably sometimes can be helpful when you have multiple regions. By the way, this work with multiple regions, just not one, like in this case you can have 2, 3, 4, 5. So usually it can be helpful because sometimes you're missing one region and so on. So just to be extra sure that you have those regions. And this step is important because this one, okay, at this point everything is separated. You see that move dynamic mesh, it works, okay, but this one is going to create the boundary conditions. So these are the ones created, required by OpenFOAM now to do all this treatment, the non-conformal treatment. So you put it there, and it is only going to do some renaming, okay, of the boundary patches. So as you go here, boundary, okay, okay. By the way, so for list times minus, you need to erase those, otherwise it's going to do it in the final one. So you go here, let me open the boundary file. So as you go to constant polymesh boundary, look at that, now you have all these new patches. So the idea of that tool is going to create this automatically. It's going to add this information. Okay, leave it to the tool to do that automatically. Even that you can do it manually, will do that automatically. And that's it. Very important, NCC1, NCC2, they need to be patches, okay? So you have to, you define as patches, follow those guidelines. Also, you have the definition of the boundary conditions. We're going to revisit that later. You follow the guidelines given by the developer. So as you see here in the output, also is going to give you some initial quality of that interpolation now between the patches, target, and source. So look at that, you have it here. So the idea is that they have to be as close as possible to 1. Okay, so here you have 128. It's not that bad, but ideally it should be 111. But that is, you have seen the mesh. There are some issues in the mesh, the mashing. Also, I didn't mention, but let me reopen here. And let me open again here. We'll open Buzzen. Okay, and there you go. So if you look closely, you have these issues here, no, in the edges of that region. So usually that mismatch that you will see is related to this. So as you get a perfect mesh, it should be 1-1 or very close to 1. Also, I think if I would recall, this is a quartz mesh. There are some issues here. So see that you have those small regions, and that can have an influence in the quality of the interpolation. So quartz mesh, as you run the fine mesh, if I would recall that, it's much better, you know, that interpolation. And actually, I think, let me go here. So logs, I don't have any log, but I have a solution. No, okay, I don't have those. In the MRF, which is pretty much the same, I think I have some logs with the NCC. No NCC, so I don't have that information. In any case, you can test it. You will see that a finer would be much better. So at this point, it has been separated. We're ready to run. Okay. So what I want to check now are the rules for boundary condition and this NCC. Okay. So in the video description, but also in the README file, okay, and also in some slides that I'm going to share, you have the link. No, so let me open here. You're going to find a few links to OpenFOAM. No, these are the links here. So here you're going to find the rules now for this non-conformal coupling, now this patching, the NCC. So I invite you now to visit, read it, digest what is written here. What is important here are the conditions now that you need to use, the definition for the boundary conditions and so on. Okay, so here you have, so very basic for the setup. Okay, something, it's not that difficult, okay, not that intimidating. So let me go here and revisit here this slice regarding the sliding mesh. So basically this is what you can do is sliding mesh. So you can have multiple bodies. Remember that this is moving here, and let me go here, and these are typical results. It's not only that for those people, I have received many requests. We need wind turbines. So here you have an application, wind turbine. Also, you can use it with particles, and look at that, you have your MAI there. It works very well. Relative motion, so motions in motions, and so on. So basically, remember that what is happening is that you create this NCC, this interface is one is fixed and the other is patched. So you have the target and the source, and you interpolate there, and that's it. Okay, so pretty much you do that. And to come back to what we did previous case, the MRF, so this is what you can get in this specific case. Look at that, we have similar behaviors, okay, very similar behaviors in the propeller that we're doing. We have the connection with the aircraft, and you will see now that the wake is not propagating, but in this case a different dynamic, so pretty much similar results. So the idea of using sliding mesh is that you want to go fully on a steady, capture all the interaction. MRF, usually you go steady, very fast solutions. You can run an MRF on a steady, but it doesn't make any sense. Usually you want to run a steady, fast sense. To start something that is not only for axial symmetry, you can have sliding meshes and interpolate like this. So this is, let's say, a train entering a tunnel, and this is a perfect case now that the sliding meshes can be very efficient for this kind of problems. I guess I need to prepare a video on that. Here you have the link now to that documentation, very important. So take some time, digest that. Some issues also post-processing with potential error with paraview. Okay, be careful, you can get those errors. So I explain a little bit there. And here we go, all the steps using a different geometry, but it doesn't matter. Okay, the steps are the same. So talking about the number of regions when you run checkMesh, then after you do the topological separation, you're going to get there 2 regions. So these are your steps: create baffles, split baffles, create non-conformal. These are the compulsory. Remember, here's where you're doing that topological splitting. Here you're going to have an explanation, and then you have some optional steps. Okay, then talking about now putting the mesh into motion and so on. Talking about now the the quality of interpolation now when patches are moving. And this is what you get also when we run the checkMesh. We're going to save, and we're going to look at that some BTK file, and you can check now the coverage. Pretty much I think that's it. Okay, to show also you can have multiple regions, and that's it. So in the video description you have the link to this slides. So let's go back to the case.